Shantanu Basu, visiting us from Western University. So Professor Basu got his PhD from UIUC, and then he did a postdoc in Michigan State University, and then a postdoc at ASIAA. And then after that, he moved to Western University in Canada, where he is now. And he's going to tell us about protostellar disks and protostellar outflow today. Please welcome our speaker.
Thank you, Minkai, for a very nice introduction and for hosting me. Thanks to everyone. It's a pleasure for me to be here with you all. And we're talking about some work that I've recently become interested in, which is launch mechanism of protostellar outflows. So I feel I'm here talking to the some of the big experts in the field. So I really I'm here to seek feedback more than anything else. This is recent work, and as I said, I'm very happy to run it by you all here, and looking forward to your comments. So let me, without further delay, mention that this is work done with my recently graduated PhD student, Mahmoud Shirkawi, and with Masahiro Mashida. We've been collaborating for several years now. So this is part of Mahmoud or Mo's PhD thesis. And we got interested in, we're interested in the problem of MHD gravitational collapse. It's a very important problem in astrophysics. It's a strong challenge in terms of the complexity of the three-dimensional physics, the vast range of scales that you have to resolve, and the physics is fascinating, but then the computational challenges are also great. And in doing some of this work, I feel we've come upon some new results on outflows that at least we were not very well aware of, and we'll see what you have to say. So I'm going to make this talk relatively short, at least by my own standards. I don't know what you're all used to, so I'm trying to keep it, within 40-45 minutes. Let's see how it goes. So I'm not giving a ton of background, but basically in this field of magnetized collapse, we've been working on this, collectively. The community have done a lot of work on this in the 80s, 90s. But then in the early 2000s, there was this very interesting paper by Alan Lee and Xu, who pointed out that if magnetic flux freezing were to hold into the very late stages of collapse, then you couldn't form a protostellar disk at all. And in hindsight, maybe it was apparent why that should have always been obvious to us, which is that if you collapse with flux freezing through a very large range of scales, you set up a very large lever arm for the inner, rapidly rotating part of the collapsing cloud to be connected to a very large radial distance further away. And that long ratio of lever arms gives you a strong torque, which would remove enough angular momentum that you wouldn't actually be able to form the disk in the first place. So in this, 1990s, 2000s graphics, the red lines are the lines that go through the red lines are the ones that go through the innermost part of the collapsing object. And they set up a relatively large lever arm that just extracts angular momentum away, and the collapse just continues. So then that spurred much work in the next couple of decades, and of course Rubin and Sieni and Zia and Lee published this and many other papers showing that if you use the standard, if you add non-ideal MHD, which is always the initial answer, well of course this won't happen because we know that non-ideal effects kick in at high densities. However, if you put the standard resistivity in, you still can't form a relatively large disk, say hundreds of AU scale, in the early phases of collapse, certainly in class 0, maybe not even later. Then there's been many other work. So for example, Masahiro Mashida, Shuichiro Natsuka, Tomoki Matsumoto published a series of papers using their nested grid code. And one of their interesting results was that there was a lot of dependence on how you treated numerically this inner region. Because the way you can get to the class 0 stage, typically, is to incorporate an inner sync cell. Why do you have to do that? It's because without an inner sync cell, you're resolving such tiny scales that your time step for stability or even just for accuracy becomes extremely small, and your calculation just grinds to a halt. And it's like Zeno's paradox. You can't get to the part that you're trying to reach. But sync cells can get you past that roadblock, but the result of the outflows certainly can often depend very strongly on how you set up the sync cell, and, how large it is, and various even issues related to the initial conditions. I won't say that we've solved that completely, but that's an important thing to keep in mind as we look at all the results. So some of the state of the art now is to use adaptive mesh refinement, where your grid essentially collapses with the flow. As you get to smaller scales, the grid is finer. So you can resolve the physics down potentially to the protostar phase. And this paper, using the Ramsey's code by Advected et al., actually, and this nice graphic shows the protostar actually forming. This is zoom in. This is the so-called second core. This is an object of stellar dimensions. And it's dragged in a lot of magnetic field. This actually has two non-ideal MHD effects included, both ambipolar and ohmic diffusion. However, the time step issue is still there. So adaptive grid gets you a lot of resolution, but you still have small time steps. So this calculation, like many others in the field that don't use the sync, that resolve the protostar, have to stop very quickly after you form the protostar. So 1 month in this case. So this is the Zeno's paradox kind of thing. Okay, we just got there, but now you can't go any further. You're not anywhere near an observed YSO, which might typically be 10,000 years old.
Could an implicit code?
We're actually working on that, but I don't know any that are published for this problem. Okay, but that is potentially a way around it. Yes, but accuracy issue is still there, of course. But still, there is a way around it. Okay, so I'm going to be talking about nested grid calculations. I mentioned the work by Mashida et al. So collaborating with Mashida, we are working on the nested grid code. And the idea here is that you have a series of Cartesian grids that are nested within larger Cartesian grids, and you keep refining. As you get to higher and higher density, you introduce another inner grid, which might have twice the resolution typically of the larger scale grid. And you keep jumping. You can go through many levels. Probably in the maximum that's been published with this code, I think, is 21 levels of refinement. I'll show you some simulations that are less because they actually include a sync. But if you don't include a central sync, you have to go typically approximately 20 levels of refinement. So 2 to the power 20 increase of resolution compared to your initial one. And many of these, initial conditions can be anything, but typically in the Mashida type work, you're talking about a critical boundary grid sphere initially, and perhaps rigid rotation and uniform magnetic field. Those can be varied, of course, and in some papers they are varied. Now, if you have a nested grid, you're going to get results that, I'll come back to this. So you may want to get a sense of, to compare with many of the traditional theories of outflow launching, which tend to be 2D, cylindrical coordinates. You may want to represent your result in some kind of angle average sense. Okay, and I'll come back to that. Now, using this code a few years ago, we published what I think is still the longest evolution if you don't include the sync. So if you resolve the protostar, so it's MHD with one non-ideal effect, ohmic dissipation. You resolve the protostar, you use a barotropic equation of state. Our next wind, but this is definitely an interaction between magnetic field of two varieties. One that's being rapidly advected in, and the other that's being diffused out. Okay, so I think I've made some of these points already. the disk itself is receiving flow from the pseudodisk wind, but further up you have an outflow from some of the pseudodisk wind that is still able to escape. Okay, this is the next to last slide. If we look at a very large scale, we can see by this time, 100,000 years almost, the outflow has gone thousands of AU. And the fact that it started within the pseudodisk helped it perhaps get this far, right? It depends on the velocity as well. But the launch point is not so close to the center, right? Much of the flow is being launched from the pseudodisk, even 100 or more than 100 AU scales. And you kind of, in the heat map of the outflow speed, the blue line just encloses where you have outflow. The white region will all have inflow. And if you look at the total mass and momentum in this region, you're finding at this time the outflow mass is about 1/10 of a solar mass, which is basically 1/3 of the stellar mass. So that kind of agrees with various analytic estimates that have been made as to how much mass gets ejected, and also various simulations in the past have suggested this. If you look at the total momentum in this region, okay, this number may not mean much to you at this time for this particular model. Okay, at 6.7 times 10 to the -2 in units of solar mass times kilometer per second. That itself may not mean much, but it turns out to be roughly the instantaneous mass of the protostar, which is about 0.3 solar masses, multiplied by the isothermal sound speed of the ambient cloud, about 0.2 kilometers per second. Put it another way, the characteristic speed is that total momentum divided by the outflow mass, which is about 0.6 kilometers per second, or 3 times the sound speed. So quick, easy calculation for people like me, who like to think simple, is if you get 1/3 of the accreted mass ejected at 3 times the solar sound speed, you're going to get 1 times m star times sound speed as the momentum in the outflow. And this, I would suggest, or we don't have proof, we haven't done it for all times, but this might be a good estimate for other times as well, at least while the outflow is active. Okay, so my point here today is if you run the non-ideal MHD to what we'd consider late times in terms of simulations, it's still only class 0, that the non-ideal MHD kind of shuts down the disk wind, and but you do get the benefit of having a pseudo-disk wind, which is launched across a variety of radii, and that pseudo-disk wind then propagates to large distances, and the driving mechanism is a hybrid of the 2 mechanisms that are normally talked about in the literature, as you would expect. We're not in either of the idealized limits that people use for analytic models. Much of what we might think is a disk wind observationally, if this model is correct, might not actually be coming from the disk. It might actually be a pseudo-disk wind that's moved to smaller radii. Okay, I'm sure this one was, and I think I'll end there and take questions. Thank you.
Have plenty of time for questions.
Yeah, thank you for a very nice talk. And we should go back to the slide for colloidal velocity field.
Okay.
Yeah, we see very complicated kinematics, and I'm wondering if you could discuss them in terms of angular momentum transfer, because at least in later evolutionary phase, some people, including me, think jet and outflows may play an important role for mass accretion by removing excess angular momentum from the encoding material, disk or pseudodisk or whatever. But for example, looking at the right figure, so in the upper layer, the flow goes out, inner layer, the flow goes in. So is there any angular momentum between those flows? Not really. Or so is that in other regions? So we don't even have to care about the angular momentum transfer. Even with that, we can just they could inflow naturally. or even in the inner region. So we see even more complicated movement, and how these might be related to angular momentum.
Mhm,
So
okay.
I'm wondering.
Okay, very good question, and I don't have a full answer, but I will say that from what we're seeing, there's not a lot of angular momentum actually removed in this
Okay.
pseudodisk way. So yeah, obviously some is, but it doesn't seem to be making a big difference. So if you look at the angular, specific angular momentum versus position, it's not changing very much. It's kind of flat. Yeah, I think in a way this is out in this region, even though you have a wind, it's still kind of like this magnetic braking catastrophe, kind of like, I mean, sorry, no, it's not. It is, it is actually the rapid dragging in of the field, and you're spinning up. And that spinning up is helping to drive the weak wind here.
Thank you.
Thank you. Just to warn that I know nothing about this field, so,
Sure.
so I'm going to ask some very naive questions here.
Please.
I'm a bit more familiar with black hole ADAS type,
Mhm.
shows where people talk about, for example, in the case of outflow, people talk about a positive Bernoulli parameter, that there's buoyancy, that the stuff that leaves is because it's very buoyant. Is that the
Mhm.
case here?
I'm not sure. I mean, I'm not sure what
So it's not-
buoyancy in this case would be.
Well, it just means that you've got
Yes.
high entropy, the combination of magnetic field and thermal entropy
Mhm.
are such that if you were just going to displace it to a higher,
Right.
a height, it
Right.
likes to, it wants to leave by itself, even in
Right.
the absence of dynamics.
Right.
Or perhaps another related question, maybe related to what we just heard, is at the end of the day, there are two ways to think about angular momentum. Obviously, stuff that goes in has to lose angular momentum. Then either the stuff going out could carry it away,
Mhm.
or you can try to propagate it out through the magnetic field lines within the disk, such that the stuff going out does not know about it. Do you know where the angular momentum ends up in this case?
Well, there is. There's definitely angular momentum going out in the outflow. What the number is, I can't tell you right now. Okay.
So I'd be curious whether that accounts for all the angular momentum stuff going in, whether you add the two up and you're done, or is it
Right.
actually something magnetic fields don't have to be local. Doesn't mean that
Right.
it doesn't have to go out with the stuff going out, but it could.
Right. I mean, there is some level of magnetic angular momentum redistribution going on in the system, particularly in the protostellar disk, even independent of magnetic fields. There is some level of that. Otherwise, the angular momentum extraction is happening through a combination of the outflow and the magnetic braking. Now, you can make a distinction between those if you like. In other words, you don't need matter to have vertical component to lose angular momentum. You can have a magnetic torque.
Well, braking means you've got a field and connecting an inner orbit to an outer orbit,
Yes.
so you're transferring your momentum to something far away.
Right.
But in a simulation, you might be able to say 50% goes in here and 50%
Mhm.
goes there.
Yeah. Right. I just don't have that number. Yeah. Good question. I'll try and get back to you.
So I have a question about radial distribution of void of field strength. I think it's a long slide before. To be clear to the previous question, so it shows like if you is accumulated on some certain values, so is the accumulated strength strong enough to hold the gas parameters drastically, or is it just strong relative to the certain region? So I'm interested in like this function process, operational process from M1 to this unit. So I wonder how drastically it changes the actual operation and the transfer.
Well, I think the magnetic field is weakened enough. It's not doing a lot in this region, but here, yes, it is important, and that is the strongest outflow launching region.
So
Okay.
do you think it's observable or is
I think that, yeah, I would like, that's I think the interesting thing about this model, that one can observe this, actually trace the outflow structure on these scales. Because, yeah, the point is the outflow is actually not emerging. Of course, we're not talking about an inner jet, which could also exist, right? And probably does. But this outflow is emerging from the disk edge, and actually a little bit outside the edge of the disk. So it's actually not emerging from this integral disk. Okay? So I think that is a potentially very interesting observational target. But as I said, if you look at low resolution, you'll see that there is a disk wind, because I'm not resolving this region. Okay? So if this model is correct, I think we need to be able to map this out observationally.
So for your introduction, you mentioned in the subcritical case, you will see counter-rotating.
Right,
Then I don't understand that. Then how that?
Okay,
what's
yeah.
that?
Okay, thanks. Yeah, I think I have a slide on this. Let me see. Yeah, let me see. Right. Okay, so. Yeah, so if you look back at these analytic models of magnetic braking by Mr. Bias and Pavialoglou from many years ago, so we take a kind of rigid rotator with a magnetic field, and now you start magnetic braking, and the angular momentum is going into the background. What happens is the angular momentum drops, but actually drops so far that you start rotating in the other direction. Okay. Now, in the model that I showed you, there was no background rotation there. Okay, so the background is not rotating at all. So now if you put a magnetic field and some initial rotation, you're twisting the magnetic field will twist the rotator back, and it won't just smoothly come back to zero. It will overshoot to counter-rotating, and it'll come back up, and you'll have a damped set of oscillations. So if you start with some rotation rate, you're subcritical. By the time you become supercritical, if you're in this part of the temporal evolution, then you're counter-rotating. And now you become supercritical and collapse rapidly, and you now preserve that sense of rotation.
Okay, it's due to the field itself is rotating in the center. Subcritical.
Yeah, in the subcritical case, the field, yes.
Then it drives
the field is, well, essentially the field is not rotating, because the background is also not rotating. And now you rotate the object, so now the field is rotating, but it pulls you back, and you overcompensate. And depending, if you become supercritical here, you counter-rotate. If you become supercritical here, you're in the same direction as the initial rotation. But you also get a weaker outflow than if you started at that rotation rate.
Can you go to the slide one before the summary?
Okay, sure.
Yeah, this one. So these relations are very interesting, but I'm wondering that the characteristic speed of the outflow here is always 6 kilometers per second, but observationally, the observed outflow velocity is much faster.
Right.
So does it mean that what the difference, what the reason
Right.
is different?
Right.
Usually, even the low velocity outflow, we have a few kilometers per second, 10 kilometers per second. So it is much faster than 0.6.
Right. Yeah, well, okay, yeah, 0.6 is the average over a very large volume. And I don't know, I mean, observationally, if you're averaging over such a large volume or not. So there is a higher launch speed at smaller radii.
Yeah, then this one is the 3 times the sound speed. Then this value doesn't change even with protostar mass increase. So then the out increase as a protostar mass increase.
Right.
But
I
this
know, yeah.
characteristic speed doesn't increase. That is, the ambient gas temperature is the same. The characteristic sound speed doesn't increase.
Mm-hmm.
Even the central mass star, protostar flows.
Mm-hmm. Mm-hmm.
So does it mean that the characteristic speed remains constant? Or
Yeah, that's a very good question. Yes, I do not think that speed would stay constant. Yes, I think the characteristic speed would depend on the state of evolution of the outflow. And as time went on, and you're spreading over a larger volume, but you're also slowing down, I think this would decrease. But the total momentum may be this value, I would claim, as long as the outflow is still being driven. I mean, at some point, the outflow itself may weaken, but you still have matter that's moving outward at large distances. So that's my gut feeling, not as an observer, but I think there will be some limited time period where this will be the instantaneous momentum, is what I would claim. This number will be changing, though, because the outflow mass is also changing.
Okay, final question?
I have a couple questions. The first one is at the beginning, you mentioned about how you choose the sync particle is quite critical. So at the end of this last case, you do have a sync particle. So I'm just wondering if the result remains robust or whether it depends on the choice of the sync particle.
Right.
And the second question is, you were discussing about all these sort of axiomatic features in the result. And so I guess the question is, can you comment on actually the importance of the 3D simulation, or whether this can be actually calculated in the 2D?
Okay, yeah, thank you. Very nice questions. Let me start with the second question. I feel now, at this moment in time, I feel that the 2D axisymmetric does capture a lot of the key features of the outflow driving. So I do feel that even though I don't think it's been calculated in 2D axisymmetric in this way, I think that all these same features would be present. I think the 3D is, at this point, based on what we see, 3D is giving you more complexity, but it's not fundamental to any of the results I've shown. Okay, but it is true. Nobody has done the 2D axisymmetric up to this phase. Okay, so I think it's a good challenge for anyone to do now, to really to incentive even to pursue the 2D because it's computationally, of course, much more feasible. As to the sync, there various people have published that there are various different codes that the sync cell does make a difference in the results, particularly when you have magnetic field. But here we do see at least a reasonable match during the first couple thousand years or so with the model that had no sync. Okay, so to the extent we can compare that early phase, they seem to more or less agree. So that's encouraging. And again, it's because the sink is small enough that the magnetic dissipation is occurring on larger scales in the sink. I think that gives us some more confidence that it's a robust result.
Okay, so I'm sorry, time is up. We don't want to run over time. Shantanu is visiting us only today, so if you want to talk to him, please do so now. Let's thank first Basu for a nice talk.
Thank you, Nick.
Vì people, but I have
think it was too. Yeah, I was trying to think. Maybe there's been in some conferences together. I'm sure. Yeah, maybe even
I
here.
used to do validation information toward and this, but we know it's not.
Yeah,
But
right.
the
I know.
technical benefit.
Right,
But
right,
curious
right.
about the field, you see it's the broken part is much stronger. The outer edge of
Yes,
the slice.
right.
This makes me curious is that because that at that point is stopping the creation from the outer part.
Right.
Because that's the yeah, I'm just curious, can we test that creation of the slice of the things and the fields, right, strengths. Yeah, to test the
Yeah, I agree. I don't know if considering these mechanisms.
yeah, it's super difficult, but I found it very interesting to see this logo on the field. It's the maximum is around
We're gonna talk about it from outside or is that
Yeah.
it's slightly
Yeah, I was
bigger,
gonna ask,
but we know
Shantanu, what
that
is-
the creation can be also not on the whole end, it can be also applying creation, so that will explain why it's not exactly. So, it's super difficult to reveal.
Right, yeah, even the best, minds are foiled, right, when you put a sort of measurements. Yeah, I mean, there was this paper, it's not a magnetic field paper, but, Felipe Alves et al. From
Oh, okay, yes,
2017.
I know.
Yeah, so they at least identified, in their case, they claim that the outflow is being launched from outside.
Okay.
Okay, they actually claim that, so that's encouraging, but there's no magnetic field information.
Yeah, it's super difficult. The other point that you mentioned about the launching point is and then the launching point is about 50 AU from the display.
Yes.
I mean,
Yeah.
having observation only we
Right.
young enough, but classroom, this is classroom, right? So then we are able to probe the motion.
I think that would be fantastic. Yeah, I would love to.
But the open label is large in this case. Yeah, I think depending on your field, about how last time on the if it's you cannot see.
Yeah, you're getting the other part too, right?
Yeah. Yeah, but the age then you know if it's a very narrow and very small opening angle, you cannot probe that. So
Right.
anyway.
So maybe if it's not as long, that's better. I don't know.
Yeah, you need to model that somehow.
Right.
I was very happy to see that as a things we can test with information to see to distinguish this green model and then we can prove the launching is maximum at the
Yes. I think
certain operation.
Right.
And then it's not on this point, it's off.
It's off, right,
That's
yeah.
one thing.
Yeah, both the disketch business and also above and
Yes,
above the
yeah,
center,
yeah.
outflow and then inflow.
Yes.
Yeah, any, I'm a theorist like that,
Yes, but
not the observation, but we're giving you something to work with.
But
right?
I'm very, I enjoy the talk a lot.
Okay.
Thank you. That's all I want to.
Thank you so much, yeah, and any thoughts, feel free to send me, you can help me, yeah. Thank you so much.
Hey, so I was curious about the specifics.